Okay, yesterday in science we started talking about the scientific method or the scientific process. What was the first step in the scientific process that scientists use to perform any experiments or to do any kind of observations? First thing I do is ask a question. What are they trying to find out? And yesterday we used the example of dropping the ball. Which ball will drop the fastest, right? That was the question. That was our first initial question. What do scientists need to do after they come up with their question? Yes, sir.
Look up
Yeah, they got to do some research, look up the information. If somebody's already done it, do the scientists need to go and do it again? No. Okay. Sometimes they need to go and look up some scientific principles. Yesterday, when we were dropping the ball, what was the scientific principle that we had to go do a little research on? Yes, ma'am.
what they are made
Okay, we could have done what they were made of, but what was it that we're talking about? What was the scientific principle when we're talking about the balls dropping? Yes, sir.
of. Their weight.
What?
Their weight.
Not their weight.
Gravity.
The gravity. Gravity is the scientific principle. What causes them to fall down? It's the gravity. So we needed to go do a little research on gravity. Then, what does a scientist do? They come up with a question, they do a little research, and then what do? Wake up. Come on. Somebody new. Yes, ma'am. Come up with a hypothesis, which is a prediction, right? We decided yesterday, a lot of people were picking, oh, I think the big ball is going to drop the fastest, the heaviest ball, the smallest ball. We came up with all of our different predictions, okay? So today, we are going to move to the next step. Once a scientist has figured out, they have a question, an inquiry, a wondering kind of statement, and then they do a little research, and they figure out which one they think is going to be the best or whatever, the next thing they got to do is actually design that experiment. And when I mean design the experiment, that means how are we going to do this? Okay? This is just like a recipe. How are you going to make bread? What do you need in order to make bread? Before you can just start making bread, you have two things that you need to figure out. What do you need to figure out when it comes to making bread? Yeah, you need all the ingredients, right? I need flour and sugar and eggs and milk and whatever else it is. I need all my ingredients. What else do you need to know to make bread? Yes, ma'am. Okay, that's part of the ingredients. How much, what kind, all that kind of stuff. All my ingredients. What else?
How long do you have to bake it for?
Okay, I need the directions, right? How do I put it together? How long do I bake it? Those are your directions. So when it comes to a recipe, you have all of your ingredients and you have all of your directions, right? Well, when it comes to science, we don't call them ingredients and directions. What do we call them? Who remembers? In a science experiment, what are all of our ingredients? All the things we need. Yep.
Materials.
Your materials, and we don't call them the directions. What do we call them in science? Not instructions, but close. They're called your procedures. Procedures means that's your big fancy science word for your directions, your instructions, okay? So in science, you need to be able to tell them exactly what they need, and you need to be able to tell them how to do it. What happens if a scientist does not give good materials? What if they just said, hey, I found the cure for cancer. All you need is a lemon, some sand, and a stick. Is that going to work very good? No. Why does a scientist need to have very, very, very good detailed materials? Why do they need to put the right material? Okay, let me go back to recipes. Why, in a recipe, they tell you, I need 2 eggs, I need 1 cup of sugar, I need 3 cups of flour, right? What if they just said, get some flour, sugar, and eggs? Will that work? Why not? You don't know how much. What happens if you put 8 cups of sugar and 1 egg in there? Are you going to make bread? Are you going to make the same bread that is in the picture? No. Science is the same thing. if you do not put the right materials in there, you're not going to come up with the same results that somebody else has already done. So a scientist has to be very, very detailed. What about the directions? When you read a recipe, does your recipe say, mix it all together and put it in the oven? Yeah, I'm done. Does that work? Why is that not going to work? Yes, ma'am. You need to know how long. What if I put it in there and I say, you know what, I'm going to mix it up and I'm going to put it in the oven for 8 hours. Are you going to get the same bread as what's in the picture? It may be burned. What else? What else could happen if you do not put good details in your procedures or your instructions? Maybe you're not supposed to mix this one with that. Maybe you're supposed to put the temperature at 300 degrees, not 500 degrees. Okay? So a scientist has to be very, very detailed. Now, let me ask you this. Is there anybody in here, is there anybody who cannot make a peanut butter and jelly sandwich? Everybody knows how? I'm hoping I picked something that everybody can do. Everybody can make a peanut butter and jelly sandwich. Perfect. You, for your homework, due Friday, is going to be make a peanut butter and jelly sandwich. Actually, you're going to tell me how to make it. Pretty simple, right? What 2 things am I going to be looking for when it comes to making a peanut butter and jelly sandwich? Yes, sir.
Peanut butter and jelly.
No.
Material?
The materials. What do I need to make a peanut butter and jelly sandwich? Okay? So I need a list, just like a recipe. I need a list of all of my ingredients to make a peanut butter and jelly sandwich. Everything, every single possible material to make a peanut butter and jelly sandwich. What else do I need to make peanut butter? What else do you need in your assignment? No, don't give me a list. What else do you need? Your procedures. So you are going to give me the list of materials to make a peanut butter and jelly sandwich and your procedures. Now, you have to be detailed. If you are not detailed, it's not going to work. Pretend like I'm from a different planet. I've never heard of peanut butter and jelly sandwich. You need to tell me how to make peanut butter and jelly sandwich. You need to list exactly how all of your materials, and you need to list and go into very good details on how to make that sandwich. Okay? Everybody understand what your assignment's going to be? It's an easy 100, right? So if you can write your materials and your procedures, and I can make a peanut butter and jelly sandwich out of your list, you got 100. Pretty simple, right? We'll see. This is going to be your challenge. It's due Friday. Back to our scientific method. After the scientist comes up with the materials and the procedures, they do it. Okay? I'm going to learn how to do my experiment, do it all, my materials, my procedures, and I'm going to actually do it. While they're doing their experiment, what are they doing? What is a scientist doing when they are actually doing the experiment? Do they do the experiment and say, have fun, watch this? What is a scientist doing? They're keeping track of it. What are they doing? They're actually analyzing their data, their results. Okay, they're gathering their data. They're figuring out, okay, well, this one was that, and that one was this, and they're writing it down, writing everything down. And what do they write it down in? They put it in a data table and a graph. Okay, so I'm going to show you here in a minute. You're going to take a data table, you're going to take all your information, your data, and you're going to put it into a graph so that you can look at this graph and analyze it better. Okay? Once a scientist has finished doing his experiment, he's graphed all of his data and he's got everything figured out, what's the very last thing a scientist will do? Okay, he'll sit back and at the very end he'll write it all down. He'll come up with his conclusion. He's going to draw a conclusion. He's going to try to figure out, okay, after doing all this experiment, what did we figure out? Okay, so yesterday we dropped those balls, right? We said which ball will drop the fastest. We did a little research on gravity. Most of you did a hypothesis. I think the heavier ball is going to drop fastest. And then we actually did the procedure, right? We actually started dropping the stuff. At the very end, we drew a conclusion. What did we kind of figure out? After doing that whole experiment, what did you figure out? That all balls will drop at the same time, right? They all drop the same because gravity is the same. So when you sit back and you analyze or draw your conclusion, what are you actually doing? First thing you do is, was your hypothesis correct? How many of you had the right hypothesis yesterday? 2 of you. How many of you had an incorrect hypothesis yesterday? Does that mean you're wrong? No. If your hypothesis is wrong, that's okay. So, was your hypothesis right or wrong? What did we learn? Well, we learned that when you drop balls at the same height at the same time, they fall at the same speed because gravity is the same, right? Last thing, if you were going to do this again, what would you do differently? What would you change? So what would we do next time? If we were going to do this again, does gravity affect these balls? What would we do? Would we just say, well, I'd change the balls? No, because that's what we just did, right? What would be something we could do differently? Yes, ma'am. Real loud. Mask is on. No, we're not going to change the hypothesis. I'm talking about changing your whole experiment. Instead of dropping the balls, we did that. What would I slightly tweak? What could we do? Maybe drop them at a higher height. Maybe if I drop them from like a 5-story building, maybe they'll start building up speed and one will go faster than the other. Could be. That's something we could try. What else could we try? Next time, what else could we try? Yes, ma'am. Different what? Not different research. It's going to be the same. What else could we try next time? Okay, maybe I'll say, wait, let's try the bouncy balls and see which one will bounce the higher. Okay, that's something we could try the next time. All right? So your steps. This is very important that you know your scientific method because starting tomorrow, I'm going to give you a lab to do on your own, and you're going to have to do all of this stuff. Okay? Okay, so for tomorrow's lab, you're going to need to know how to do a data table and a graph. Okay? So this is a data table. Data table is a way to put all of your information in there quickly. This is like taking notes or whatever. Okay? So here you can see I'm going to do a new experiment real fast so that we can get some data. We're going to take that same soccer ball, the bouncy ball, and the marble, and this time I'm going to roll it down a ramp, okay? Because I want to see which ball will roll the farthest, okay? So I would do some research. If I was doing this, I'd do some research on maybe friction or maybe motion or something that has to do with science of what's about to happen, okay? Then I would take my hypothesis. So I'll get a quick, how many of you think this ball will roll the farthest? Not the fastest, the farthest. Real high. 1. How many of you think this ball is going to roll the farthest? Quite a few of you. How many of you think the marble is going to roll the farthest? A couple of you. Okay, so if I was doing this, my materials and procedures would be, you need a foam soccer ball 4 inches in diameter. You need a bouncy ball 2 inches in diameter, and you need a marble that's 1 centimeter in diameter. You will need 3 math books. You'll need 3 metric rulers. You will need 1 clipboard as a ramp. Okay, so I gave you my materials. My procedures are going to be, take 1 ball at a time, starting at the same place on the ramp, roll it down the ramp, measure how far it goes. Do each ball 3 times and then take an average. Okay, everybody understand what we're doing here? So I'm going to do this real quick just so we can get some information, and I'm going to put it in there. So we're going to start with the soccer ball, and we're going to roll it down 1 time. Okay. So again, starting up here at the same place, I roll it. Now, is that fair?
No.
It hits something. Is that fair?
Yeah.
Should I count this?
No.
No. I'm going to do it again. And this is part of doing the experiments. If it doesn't work right, Sometimes you have to kind of do it again. So here I do it, and it rolls to about 260. 260 centimeters. Now, notice we're doing it in centimeters because we do everything in science in metric, not inches, not feet, not yards, meters, centimeters, that kind of stuff. Why am I doing it a second time?
Because we're trying to.
Why do I do it again? That
Because
one was
you
about
just see if
220.
it's
We're trying
to
to.
see if
Why do I do it 3 times? Length? Right, I make sure I do it right. Because if I'd have just done it one time and it hit the wall like that, did I do it right? Would that be fair? No. So we're going to do it 3 times just in case there's something weird that makes this, like this, just hit the meter stick. I'm not going to count that one. It's not fair. Got to go without hitting something. All right. And that one goes, 290. All right. Are those pretty close to each other?
no.
260, 220, 290. I mean, they're all within a few centimeters. Not that far distance. That's pretty close. Would it be fair if I had 260, 220, and then 50? What would that 50 mean? Something happened wrong, so I would probably need to redo it, okay? But since those are all pretty close, I'm good. I'm going to do the same thing with the bouncy ball. 3 times. That would be 100 and, nope, right at 200. 3 times. About 295. That's what I meant. 195. And that one is going to be about 195 also. And finally, the marble. 130. $35. $40. Okay. Now I've done it 3 times, and I have one more column over here. What's this column for? Average. How do I come up with the average?
Add
No. How do I come up with the average? Like when we're doing your grades, I take all of your grades on all of your homework. I take all those grades and I come up with your average. What do I do? Okay, first thing I do is add them all up. So if I did 260 plus 220 plus 290, 770. Is that the average of them? No. That's like your homework. Do I give you, you got a 90, a 90, an 80, a 100, 90, and all of a sudden your total is your grade 560? No. You have to do one more step. What do I do after I add them all up? By what? You divide it
By how many times you did it?
by how many I have here. I added 3 numbers together, so I divided by 3. So the average, I'm going to round that, is to 257. Okay? If you do it right and you average, your average will always be somewhere between your biggest and your smallest. Okay? So let's do the next one real quick. 200 plus 195 plus 195 equals, divided by 3 is 197. And the last one, 130 plus 135 plus 140 divided by 3 is 135. Okay? I have a data table, right? Can you tell me real quick, just by looking at this, like how much better the one is than the other? Can you see it very good like this? It's just a bunch of numbers if you ask me, right? We need to put it into something, some form, some way that it looks visually good or better to see which one is higher or lower and things like that. What could I do that would be visually appealing that makes it a lot easier to see? Put it in a graph, a chart, right? Okay, so tomorrow we're going to take this data, and I'm going to show you how to make a graph. And then we will do our own experiment. And you're going to have to come up with your own data. You're going to have to graph it. You're going to have to come up with your conclusion, your hypothesis. We're going to do a regular experiment tomorrow, all of us together. Okay? Once you get a data table written, then you got to turn it into a graph. So on these graphs, there's a few things that you have to make sure that you have. One is the title. It makes it real easy from the data table. It's the same title as the data table. So this graph is going to be called the type of ball versus the distance traveled. Okay? If you don't have the title, it will be wrong. Down here you can see there's 3 spaces. These 3 spaces are for your 3 different variables, the things that are different. So we have a soccer ball, we have a bouncy ball, and we have the marble. Now a lot of people just put those 3 and they miss a point because they need to title these. You have to have a title, that's why I have a little circle down here. This little bubble is for the name of those. So what we could call this is the type of ball. This right here is what you're measuring. This, and since we're measuring the distance it travels in centimeters, again, you have to label that the distance traveled in centimeters. And if you notice, when it comes to the title, the type of ball is down here, and the distance it traveled is over here. So your title is based on the 2 sides, the x-axis and the y-axis. The last thing you see here is this. This needs to be your scale of what you're measuring. Well, if you look, our biggest number is 290, and our smallest number is 130. So our scale should be between 130 and 90. So to make this a little, to make it better, you gotta pick the right scale. The best scale to pick is to go by ones. 1, 2, 3, 4, 5, 6. But if we did that, this graph would be way too big. You'd have 290 lines. Try 2s. Again, if we did 2s, it would be too big. 5s would be too big. 10s would be too big. Looking at this, to me, I think 50s would probably be the best bet. 50, 100, 150, 200, 250, 300. At this point, you're then going to go ahead and plot in your bars. And if you notice, according to our legend, we have the 3 trials and the average, and we're going to color code them so that you can kind of see them a little better. So if I went to the soccer ball, my first one is 260. I would draw a black bar up to 260. I would have a yellow bar, which is trial 2, at 220, which would be a little bit less. Then I would do 290. Red, almost up to the 300. And then, of course, my last one is the average, and it's going to be 257. And if you do this correctly, your average should always be somewhere between your tallest and your shortest lines. We're going to continue with the bouncy ball again. Bouncy ball, the number is 200. Then it was 195, so just a little bit less. And then 195, same. And then our average was just a little bit more, but still between our tallest one and our smallest one. Finally, the marble, 130. So our first one is about here. Our second one is just slightly above it. The last one's 140, which is slightly above it. And then, of course, our average is between the tallest and the smallest, which is 135 right here. Now, the reason we put this into a graph is because it makes it so much easier to read the data. This is just a bunch of numbers. It's hard to kind of tell, but this graph, you can now easily see, look, the soccer ball, all of these numbers are higher than the bouncy ball and then the marble. So you can kind of see visually a lot easier, a lot better than what all this numbers and data is going for. But remember, when you take your Data table, make sure you have titles. You label, you have a good scale here, and you label down here, and then you accurately plot each line.